Hello guys, welcome back to another Chem cell potential video. And in the previous video we talked about standard cell reduction potentials, which means hello guys, welcome back to another video on cell potential Chem 2C stuff, chapter 11. In the previous video we talked about the standard reduction potential, and one important thing to know about those is that when we talk about standard stuff in chem, usually means at 25 degrees Celsius, which is the standard temperature. And then this time around it's also at 1 molar. So the cations in the cell potential is at 1 molar and it's at 25 degrees Celsius. But then what happens if this concentration changes? That's what this video is going to be about. When the concentration of the solutions in the cell reaction either increases or decreases. Before we get into that, however, I'm going to give, let's say, a random cell reaction. So right here, Al, this is 2s plus 3Mn, 2 plus aqueous goes to 2 aluminum, 3 plus 3 Mn solid. And with this equation, you can figure out what the galvanic cell will look like which is the anode, which is the cathode, and you do that by figuring out which is getting reduced and which is getting oxidized. So Al over here, aluminum, we can notice that it goes from a charge of 0 to a charge of 3 plus. So that means aluminum is getting oxidized. The charge is being increased. And remember what we said, according to galvanic cells, if an element is getting oxidized, that means it is red ox. So was it red cat and ox? Yeah, red cat and ox. So oxidized is anode. So over here, the Al is the anode, and then on the right side of the reaction, since this is getting oxidized, this has to be getting reduced, which it is. I think this is manganese. Manganese over here goes from a charge of 2 plus to a charge of 0, so it's getting reduced, which means it has to be the cathode. That's just a key thing to realize. And if you're given a galvanic cell and you're like, you know which one's getting oxidized, which one's getting reduced, you can write out the whole equation just based off that. Just put the one that's getting oxidized, starting with a charge of 0, going to increasing, and the one that's getting reduced, start on the reactant side with the positive charge, and then go into a 0 since it's getting reduced. And now, with this information, if you remember from, let's say, I think the Gen Chem 1, the first Chem series, in this reaction, I think Le Chatelier's principle, if the concentration of the reactants, so the one on the left side, these two reactants, if the concentration of this reactant goes up, that means the equation has to move. So equation, whatever power, what's the word for it? I can't remember the word, but spontaneity moves towards the side with less concentration. You're going to see that concept come out again in the future. But if we increase this side to balance it out, this side has to increase as well. So the reaction is going to move to the right. The reaction is going to move to the products. And moving to the products is a spontaneous reaction. So that's why the E is going to go up, which means we're creating more of the product side. So E is going to go up. The spontaneity, spontaneous is going to go up. And we're only looking at the sides with the cations. Here, I'll erase it and highlight it. We're only looking at these, so the ones with a 2 plus, this doesn't have a 2 plus, and we're looking at these. These are the two elements in the reaction. So when we say it moves over to the product side, that means this side, the cation in the product, is getting increased. So that means when we increase the concentration of this concentration has to increase as well. And then the other way around, when you increase the concentration of the products, then the E goes down. So when you increase this side, here, draw it again. When you increase this side has to increase as well. So that means when the reaction will move over to this side. And when the reaction is moving towards the, usually we want reactions to move towards the product because, the arrow showing is moving. That's just an inherent thing or an idea that helps me remember it. So that means if it's doing the opposite, that means the energy is going down and the spontaneity is also going down. And that's an important thing to remember. So now I'm going to ask not a bunch of questions, just 2 different questions. So let's say in this reaction, you're given the aluminum is equal to 1 molar and the manganese is equal to 3 molar. So they were both initially 1, but then this increased. What would happen to the reaction? Okay, so since we look over here to the equation, since this side, the reactant is being increased, that means, like we said here, the energy would increase here. And when the energy increases, it means the product side would increase as well. So this concentration will increase as well. I guess when I say concentration like this, which means the reaction would get more spontaneous since you're increasing the reactant. And then if you do the opposite, if the aluminum concentration becomes, let's say, 3 instead, while the manganese is still 1, then you look at this equation, you just seen that the product side got increased. So that means the reaction would reverse, move towards the reverse, which means it'll move towards the reactant side and move this way, and the energy would decrease, and it'll also become less spontaneous, and this concentration would increase since it's moving over to the reactant side, and this is a reactant. Now we figured out how concentrations work. In these, I'm gonna move over to something called concentration cells, which is, I'll write it down. And in these concentration cells, what it just means is that it's the same element. So this, let's say, for example, like, let's use aluminum again. It's the same element, aluminum, but this time, like, so both sides of the galvanic cells have aluminum Al3+, so the cation of aluminum as the solutions, but one of them has different concentrations. So for example, this one has 0.1 molar, or this one has 1.0 molar. And in these, energy would still transfer, although not as much because it's the same element and they have the same standard reduction potentials. But since the concentrations are different now, there would still be energy or electrons being transferred to try to, balance out this equation. Just like how if you have an equation like this with different concentrations, it might have been the same element, but then they still, Le Chatelier's principle, try to balance both equations out. And in a concentration cell, usually the concentration, or what I say, the reaction moves towards the cell with less to a cell with more. And by reaction, I mean electrons. So in a galvanic cell, say they both have aluminum in them, Al3+, Al3+, and this is 0.1 molar, and this is 1.0 molar. This is going to be the anode on the left, since that's the side the electron is losing, and then the right hand side is going to be the cathode, and the electrons are going to transfer from here, from the anode to the cathode. And I'm going to write out an equation to help you remember this identity. So let's say Al, since this side is anode is getting oxidized, it will be on the left. Al3+ would go, this is aqueous. And I also label the concentration 0.1 molar plus this solid aluminum of the 1 molar. I don't even have to add it, but I'll just add it so it's easier to see. And then it's gonna go, so oxidized, I got it flipped actually, since oxidized the element, the anode is being oxidized, so it starts at 0. So this is the one with 0.1 molar, and then this is the one with 1.0 molar. And then it becomes, since the anode is getting oxidized, so the side with less molarity over here, less concentration, is getting oxidized. So it has to go from a charge of 0 to +3. LL 3 plus 0.1 molar. And then the side, the cathode, the side with more concentration, so 1 compared to 0.1, is getting reduced. Since cathode gets reduced, so it's going to go from charge of +3 to 0, so it's losing 3 charges. It's getting reduced. Plus AL with a charge of 0. And it's a solid now, 1.0. And if you can see from this equation, the reason why, I'm going to highlight the key parts of this reaction. So the cations, the part that's seen in the galvanic cell right here, the cations, they're both cations, are the key parts of this equation. And this makes sense, and the reason why is because, as you can see, if you remember Le Chatelier's principle, things go from high concentration to low concentration. Wait, let me, instead of, usually the upside means, so I'm gonna write high instead of that. It goes from high concentration to low concentration, because it's trying to balance out. Like if you had a container full of water, you had another container with barely any water, and you put them together, it's going to give you right in the middle container with in the middle medium amount of water, because those two, the high water is going to go to the low water to balance it out. And that's the same thing with reactions. Oh, I was trying to erase it. In reactions, it's going to go from the higher concentration to lower reaction to lower concentration to try to balance it out. And right here, if you look at the cations, it's observing that rule. It's going from the higher concentration, and then it becomes, in higher concentration, remember we're focused on the cations here, high concentration to lower concentration. And that's why the electrons flow from the anode to the cathode. And that's why, no, obviously electrons flow from anode to cathode, but that's why we put the less concentrated one in the anode. Because if you write it all out in the equation like this, you should see that the side with more concentration should be a reactant, and this side with less concentration should be a product. So it makes sense that the electrons are going to move this way, which is why, or how to remember, that the E moves towards the cell with less, E moves towards the cell, I wrote that wrong. The electrons move towards the cell with more, I did write that down wrong, with higher concentration. So for example, if you're given this equation, if you're given this like reaction, Fe goes to Fe 2 plus the concentration of 5 molars plus 2E, and this one as well, Fe, the same thing, Fe 2 plus, but a concentration of 1.0 molar plus 2E. How you'd write it is, this side is going to be the anode, because it has less concentration, and then this side is going to be the cathode. In the next video, I'm going to talk about the Nernst equation, which does help explain this better. But if you're having troubles remembering which is the anode, which is the cathode, write it out as a full equation, and then the side with more concentration should be on the left. And if it's on the left, you know that the cation has to be on the left, and then the regular metal has to be on the right. So you know that it's the one on the left is getting reduced, so it goes from 3 to a 0 charge, and if it's getting reduced, it has to be the cathode. So it's like a puzzle piece. If you just write it out from this, you can find out which is the anode and which is the cathode from writing it out. If you remember, higher concentration goes in the reactants for it to be spontaneous, and the lower concentration goes in the products for it to be spontaneous, which means the ones with less concentration goes on the product side. Right here, the cation goes on the product side, and if the cation is on the product side with a positive charge, that means the reactant version of it has to have a 0 charge or a solid, which means it's being reduced. And if it's being reduced, it's the anode. That's the side with the lower concentration, the anode. I just wrote this to help you remember and be able to tell the difference, because this is probably going to be a multiple choice question in both midterm and final about which side is going to be the anode and the cathode in the same concentration cell. I mean, same same element with different concentration cell.